Okay, hello. All right. So this video is going to be a few example problems on chapter 5, specifically on magnetic flux and induced EMF and induced current. So let's do this first question. A 50-turn rectangular coil of dimensions 2.5 centimeters times 10 centimeters is allowed to fall from a position where B is equals to 0t to a new position where B equals to 2.5t, and the magnetic field is directed perpendicular to the plane of the coil. Calculate the magnitude of average EMF that is induced in the coil if the displacement occurs in 0.25 seconds. So the number of turns here is 50 turns. The dimensions 2.5 times 10 refers to the area, so that's going to be 2.5 times 10. Then I have cm square, right? And that is going to be 2.5 times 10 is 25. Cm square is times 10 power of -4 m square. That's all in SI units. And then my initial B is actually 0 Tesla, and then my final B is 2.5 Tesla. The magnetic field is directed perpendicular, so top view, if I have my plane, let's use red for plane, right? If this is my plane and I have magnetic fields going this way, all right, so this is B, and then I have my my area vector pointing this way, right? We can see the angle between the B and A is actually 180, or you can also use 0. It will yield the same magnitude. Okay, same magnitude. So I can write down here that the angle, let's just use red, the angle between A and B is actually 180 degrees. We can do that, or 0, whichever is fine. So then we can solve this problem if we remember Faraday's law. Faraday's law says that, the induced EMF is actually equal to d phi over dt. Okay, well, if we include Lenz's law, then you have a negative. So, but I'm not worried about that because it's only asking for the magnitude. So then I can expand on phi. So d over dt, which is just n times b times a, and then the angle between them, right? So it's a cross product, so we will have sine theta. Okay. Sorry, it should be cos theta. Cos theta, that is for cross product. Okay. All right, so let's not make that mistake again. I will just write down the notes here. A cross B is equals to the magnitude of A times the magnitude of B times cos theta. It's always useful to just have footnotes like this as you go through questions, so that when you revisit those questions, you are reminded of it. Okay, so my epsilon is going to equal to, okay, number of turns doesn't change, so I can bring it out the front. Let me just use a better color. I can take out n, right, and I can take out a, but I have to maintain b. The angle also doesn't change, so I can move it to the front as well. Basically, n, a, and theta doesn't change, so that means my n, a, cos theta is at the front, multiplied with the rate of change of magnetic field. Because the rate of change is relatively small, right, we can substitute it or change it to delta B over delta T, which is B final minus B final minus BI, B initial, right? So then I have epsilon equals to NA cos theta B final minus BI over the time taken, which is just T final. If I substitute those values, I will have 50 times 25 times 10 power of negative 4, that's the area, and then cos 0 is 1, then multiplied by the final magnetic field, which is 2.5 minus 0 over 0.25. okay, so if you key that into your calculator, what you will find is that the magnitude of the average EMF produced is 1.25 volts. So it's going to be 1.25 volts. Okay, so that is my final answer for problem 1. Okay, so now we want to look at the next question, which is question 2 or problem 2. We have, let's just read the question. A 528 loop circular armature coil with an 8 centimeter diameter. Let me just highlight the information, right? Okay, 8 centimeter diameter, rotates at 60 revolutions per second in a uniform magnetic field of a strength of 0.55 Tesla. Determine the peak induced EMF. So I would like to remind that Faraday's law simply says that the induced current is equals to the negative of, not negative, that's Lenz's law. So Faraday's law just simply means that it's going to be equal to d phi over dt. d phi is the change of magnetic field. If we were to expand on this, I will have d over dt and BA cos theta being the angle between the B and the A. Now, the interesting part about this one is that it is rotating. So when it is rotating, my NBA remains the same, but I will have to differentiate cos theta. So cos theta, the way to differentiate this is to remember that you have theta is equals to omega t, right? This is in radians per second, right? This is in seconds, so I'm left with radians. So then if I expand on that, I'm left with epsilon equals to and BA, so differentiate cos theta, but instead of having cos theta, I will have cos omega t. And when you differentiate this, what you will get is NBA omega sine omega t. Okay, so because it says peak, right? Let me just, okay, because it says peak, right? If it says peak, that means my sine omega t is going to be equal to 1. It's the biggest value because sine omega t can take values between 0 and 1. The biggest one is 1. Okay, so then what I'm left with is that epsilon is equal to and B A omega, but this is only if epsilon max. So there's a few things that we need to know. N is just 528, B is given directly 0.55. However, A must be calculated, and A, because it's a circular loop, I will have pi r square, right? And R is just half of D, so I'm left with D over 2 squared. And then I have omega, which is expressed in 60 revolutions per second. I need to convert that to radians per second, so that means I have to multiply it by 2 pi. Okay, so then when I substitute all those values, I will have epsilon max is equals to 528 times 0.55. I have pi and then I have my diameter, which is 0.08 divided by 2, and then that is squared, and that whole thing is divided. Oh no, there's no division. Nice, there's no division. So I have, let me just recheck everything. I have N, I have B, I have A. Oh, I don't have omega. So I need omega. Omega is 60 times 2 pi over 1. That's just radians per second. So this is omega. It's best for us to always check that we've substituted those values, right? So you can key this into your calculator and you will get 550.298 volts, and that is my final answer. All right, so let's move on to the next question. Okay, so let's look at the next question. A circular loop in the plane of the paper lies in a 0.8 Tesla magnetic field pointing into the paper. Okay, the loop's diameter changes from 15 centimeters to 4 centimeters in 120 milliseconds. What is the direction of the induced current, the magnitude of the average induced EMF, and the average induced current if the coil resistance is 1.25 ohms? Okay, so just to make our lives easier, let us just draw from the top view. If we view it from the top, all right, and then we have the piece of paper. So here's a piece of paper, and then the magnetic field. It is pointing into the paper. So into the paper, we will see crosses like that all around the paper, and then I have a circular loop. So let's just draw that out. I have a circular loop. Okay, and then what we have is the magnetic field is equals to 0.8 Tesla, and then the diameter changes. Sorry, okay, so the diameter changes from 15 cm to 4 centimeters. Of course, we can quite easily calculate the area, right, which is just equals to pi d square over 4, which is pi r square, by the way. Okay, and I can quite easily say that the change in area is actually, so pi over 4, and then d square, which is 0.15 square minus 0.04 squared. Okay, so first things first, we need to figure out what is the direction of the induced current. So the original, let's draw it out. The original direction, right, of B is going into the page, and then when it shrinks, there's less magnetic flux, right? So it has to be the opposite. So the change is going to be in the opposite direction, and to counteract with this change, the reaction, so Lenz's law will react by maintaining it, right? So if it's going into the page, the direction of the current is going to be clockwise. So clockwise. Answer for the first one is clockwise. How do I know that? Is if I use my right hand and I point my thumb according to this Lenz's law, right, I will see that all other four fingers, my forefinger, my middle finger, and the rest of my fingers will point in the counterclockwise direction. So that's how I determine it. I need three things. I need the original magnetic field, and then I need the change, which is the red one, the change of it, either it increases or decreases the magnetic flux, and then I apply Lenz's law by doing the opposite of whatever that change is. Okay, all right, and then my time, I'll continue on with the question. right? I'm looking for the average induced EMF. I'm looking for my time, which is 120 times 10 power of negative 3, which is 0.12 seconds. So we've determined the direction of induced current. My answer is clockwise. Clockwise. I'm looking for the magnitude of average induced current, which is just epsilon equals to d phi over dt. D phi is defined by BA cos theta, right? But the B doesn't change, so I can take it out. So B, I can take it out. I have cos theta. Theta doesn't change as well, but my A does change, right? So my A changes. So then I can substitute the values. Since the circular loop is just placed on the paper, the angle between circular loop and the paper will simply be 0. So this is going to be 0. That means cos 0 is 1. So then I'm left with just b, 0.8. Then I have to multiply it by the change in area. So pi over 4, 0.15 squared minus 0.04 square. Okay, and then that whole thing is divided by the time, which is 0.12. Okay, so then the magnitude of my induced current, if you key that into the calculator, to your calculator, is going to be 0.109 volts. Okay, so that is my final answer for B. And then we can proceed to average induced current, right? Just remember that we can just apply Ohm's law here. So that means my epsilon induced is equals to my I induced times R. My R is 1.25, so that means my I induced is equals to epsilon induced over R, which is simply 0.109 divided by 1.25 ohms. Induced. Okay. And thus my induced current will be 0.087, which is 87 milliamps. So 87 milliamps. And that is my final answer for the third part, which is just the magnitude of induced current. Okay, proceed to the next question. Okay, so let's look at problem 4. All right, a circular coil of 180 turns with a plane area of 12 times 10 power of negative 3 meters square is placed in a region of 0.35 Tesla magnetic field. Calculate the magnetic flux linkage through the coil when the plane of the coil makes an angle of 30 degrees to the magnetic field. Okay, there's a few things that needs to be addressed here. Let's just write down the information given, right? So the number of turns, we would have 180 turns. The area, we will have 12 times 10 power of negative 3. So when we do this, we want to make sure that all the units are in SI units, all right? And then my magnetic field strength is 0.35 Tesla. Okay, this is a very important part, right? When we talk about angle theta, it is between the area vector and the magnetic field lines. Okay, if I were to draw from a top view, I will see that the magnetic field lines, let's use blue for magnetic field lines. Okay, I will have blue magnetic field lines like that. Okay, and then if my plane makes 30 degrees, right? So let's have our plane to be purple. Okay, so I have my plane 30 degrees from the magnetic field lines. So this is the blue one is my magnetic field lines, then my purple, the purple is my is my plane. You have to remember that the area vector is perpendicular, right, from the plane. So this is my area vector. Okay, so then the question begs, what is the angle between the area vector, let's just use green for that, what is the angle between my area vector and my magnetic field, which is this one? Okay, that is the angle that I want to look for, or specifically I can use this one, it's the same ones. Now if you remember, if I have two lines in probably secondary school mathematics, if I have two straight lines, so let's draw them like that. Okay, this angle theta 1 is actually equal to theta 2, right? Theta 1 equals to theta 2. What that means is that this part is also going to be 30 degrees. I know the sum of it, I know the sum of it must be 90, right? Its counterpart is 30. So that means the green one here is going to be 60, because 90 minus 30 is 60. So that means the angle between vector A and vector B is actually 60 degrees and not the given 30 in the question. Okay, all right, so the angle between the plane and magnetic field is 30. Okay, so there's another way of writing this, which is if I have okay, so the angles, right, I can find out what's the angle between vector area vector and the magnetic field if I simply minus out 90, minus out the angle of the plane to the magnetic field, right? 90 minus 30 is 60. Okay, so then when I want to calculate my magnetic flux linkage, I'll just use black at this point. Okay, when I want to calculate the magnetic flux linkage, which is equals to n phi being and phi, my n and my phi is actually b a cos theta. This theta is the angle between area vector and the magnetic field. Okay, so then I have 180 turns, my b is 0.35, my area is 12 times 10 power of negative 3, then the angle between them, so cos, the angle between them is actually 60 degrees, right? So then I have my magnetic flux linkage is equal to 0.378 Weber. So 0.378 Weber. And that is my final answer for this question. Okay.